Today we are going to learn about advanced matrix decompositions with NumPy. We will explore various decomposition techniques and their applications, focusing on enhancing your skills in implementing and applying these methods to solve complex problems efficiently. Matrix decompositions are a set of techniques used to factorize matrices into simpler, constituent parts. These methods are of paramount importance in various computational fields, providing the backbone for solving linear equations, performing data compression, and tackling eigenvalue problems. In this segment, we'll provide a brief overview of various matrix decomposition methods and their applications. We'll also introduce you to the powerful capabilities of NumPy, a library that makes it easy to implement these techniques efficiently. Singular value decomposition, SVD, is a crucial matrix factorization technique that expresses a matrix as the product of three other matrices. Formally, for any matrix A, SVD represents it as A equals UV, where U and V are orthogonal matrices and is a diagonal matrix containing singular values. SVD is particularly useful in the fields of data science and machine learning. It facilitates tasks such as dimensionality reduction and noise reduction. We'll delve into how SVD works, its mathematical foundations, and practical applications. Furthermore, we'll demonstrate how to implement SVD using NumPy, which offers efficient computation even for large datasets. Eigenvalues and eigenvectors are fundamental concepts in linear algebra, crucial for understanding the properties of matrices. An eigenvector of a matrix is a vector that does not change direction during a linear transformation, and the eigenvalue is the scalar by which it is stretched. These concepts are vital in various applications, including stability analysis, vibration analysis, and quantum mechanics. In this section, we'll explore the mathematical significance of eigenvalues and eigenvectors, and demonstrate their computation using NumPy's eigenfunction. We'll also discuss real-world applications where these computations play a pivotal role. Cholesky decomposition is a specialized matrix factorization technique applicable to symmetric, positive definite matrices. It decomposes a matrix into the product of a lower triangular matrix and its conjugate transpose. This method is more efficient than Lie decomposition for this class of matrices, making it a preferred choice in various applications. In this block, we'll delve into the mathematical basis of Cholesky decomposition and demonstrate its implementation using NumPy's numpy.Linelj.Cholesky function. We'll also explore its applications in optimization problems and numerical simulations, highlighting its significance in computational efficiency.
QR decomposition is a matrix factorization method that expresses a matrix as the product of an orthogonal matrix Q and an upper triangular matrix R. This technique is widely used for solving linear systems, least squares fitting, and eigenvalue problems. In this segment, we'll break down the mathematical principles behind QR decomposition and showcase its implementation using NumPy's QR function. We'll also discuss its applications in machine learning and data analysis, where QR decomposition serves as a robust tool for various computational tasks. Dimensionality reduction is a critical process in data science, aimed at reducing the number of random variables under consideration. This simplifies models, reduces computation time, and often enhances performance. Singular value decomposition, SVD, is a powerful tool in this context, particularly when applied in principal component analysis, PCA. We'll explore how SVD aids in reducing the feature space while retaining essential data characteristics. This block provides practical examples and demonstrates the application of SVD in real-world data scenarios, emphasizing its role in improving computational efficiency and model performance.
Numerical stability and precision are crucial factors in computational mathematics. When dealing with large datasets and complex calculations, maintaining stability and precision is vital to obtaining accurate results. In this section, we'll discuss the importance of numerical stability, the challenges posed by floating-point arithmetic, and how these issues can affect computation results. We'll also highlight how NumPy provides tools and functions to mitigate these challenges and ensure stable and precise calculations. Techniques for enhancing precision in matrix decompositions will be discussed, equipping you with the knowledge to handle computational tasks more effectively. Matrix decompositions play a pivotal role in machine learning and data science, serving as the foundation for various algorithms and techniques. They are extensively used in data compression, feature extraction, and improving model performance. In this block, we'll explore specific use cases where matrix decompositions enhance machine learning workflows, particularly in handling large datasets and extracting meaningful features. We'll also discuss how these techniques contribute to data compression, making it feasible to manage and analyze big data efficiently. By understanding these applications, you'll gain insights into integrating matrix decompositions into your data science projects effectively. Latent semantic analysis, LSA, is a technique in natural language processing that leverages singular value decomposition, SVD, to analyze relationships between a set of documents and the terms they contain. It identifies patterns in the data and improves information retrieval by capturing the latent structure in term document matrices. In this segment, we delve into how SVD is employed in LSA, enhancing text mining and processing capabilities. We'll demonstrate the implementation of LSA using NumPy and discuss its benefits in improving text processing tasks, providing a deeper understanding of its application in real-world scenarios. Integrating matrix decompositions into Python projects requires a strategic approach to ensure computational efficiency and accuracy. This block focuses on best practices for incorporating these techniques using NumPy, optimizing your code for performance, and handling large datasets effectively. We'll provide practical coding examples, demonstrating how to apply matrix decompositions in real-world scenarios. By following these guidelines, you can enhance your Python projects, ensuring robust and efficient computation, which is crucial for tackling complex data analysis and machine learning tasks. In conclusion, mastering matrix decompositions is essential for professionals in computational fields, providing the tools necessary for efficient problem solving and data analysis. We've covered key techniques such as SVD, eigenvalue computation, and QR decomposition, exploring their applications across various domains. The skills acquired in this video will empower you to implement and apply these methods effectively in your projects. We encourage you to explore these techniques further, as they form the backbone of many advanced computational tasks, offering endless possibilities for innovation and discovery.